In mathematics, an associahedron knot is a dimensional convex polytope in which each vertex corresponds to a way of correctly inserting opening and closing parentheses in a word of n letters, and the edges correspond to single application of the associativity rule. Equivalently, the vertices of an associahedron correspond to the triangulations of a regular polygon with n+1 sides, and the edges correspond to edge flips in which a single diagonal is removed from a triangulation and replaced by a different diagonal. Associahedra are also called *F polytopes after the work of Jim *F, who rediscovered them in the early 1960s after earlier work on them by Dovtamari. Examples: the one-dimensional associahedron K3 represents the two parenthesizations Z and A three symbols, or the two triangulations of a square. The two-dimensional associahedron represents the five parenthesizations of four symbols, or the five triangulations of a regular pentagon. It is itself a pentagon. The three-dimensional associahedron K5 is an enneahedron with 9 faces and 14 vertices, and its jewel is the tri-augmented triangular prism. Realization. Initially, Jim *F considered these objects as curvilinear polytopes. Subsequently, they were given coordinates as convex polytopes in several different ways. See the introduction of Sebellos, Santos and Ziegler for a survey. One method of realizing the associahedron is as the secondary polytope of a regular polygon. In this construction, each triangulation of a regular polygon with n+1 sides corresponds to a point in dimensional Euclidean space, whose ith coordinate is the total area of the triangles incident to the ith vertex of the polygon. For instance, the two triangulations of the unit square give rise in this way to two four-dimensional points with coordinates n. The convex hull of these 2 points is the realization of the associahedron K3. Although it lives in a four-dimensional space, it forms a line segment within that space. Similarly, the associahedron K4 can be realized in this way as a regular pentagon in five-dimensional Euclidean space, whose vertex coordinates are the cyclic permutations of the vector where phi denotes the golden ratio. Because the possible triangles within a regular hexagon have areas that are integer multiples of each other, this construction can be used to give integer coordinates to the three-dimensional associahedron K5. However, this construction in general leads to irrational numbers as coordinates. Another realization, due to Jean-Louis Lode, is based on the correspondence of the vertices of the associahedron with n-leaf-rooted binary trees. Indirectly produces integer coordinates in dimensional space. The ith coordinate of Lode's realization is aibi, where I is the number of leaf descendants of the left child of the ith internal node of the tree and bi is the number of leaf descendants of the right child. It is possible to realize the associahedron directly in dimensional space as a polytope for which all of the face normal vectors have coordinates that are 0, +1, or -1. There are exponentially many combinatorially distinct ways of doing this. Because K5 is a polyhedron only with vertices in which 3 edges come together, it is possible for a hydrocarbon to exist whose chemical structure is represented by the skeleton of K5. This associahedron C14H14 would have the Smiles notation. C12, C3, C4, C1, C5, C6, C2, C7, C3, C8, C4, C5, C6, C7, 8. Its edges would be of approximately equal length, but the vertices of each face would not necessarily be coplanar. Number of K-faces. The number of dimensional faces of the associahedron of order n is given by the number triangle AO33282, shown on the right. The number of vertices in knots +1 is the nth Catalan number. The number of facets in knots +1 is the nth triangular number -1. because each facet corresponds to a 2 subset of the n objects whose groupings form the Tamari lattice Tn, except the 2 subset that contains the first and the last element. The number of faces of all dimensions is a Schroeder-Hipparchus number. Diameter. In the late 1980s, Daniel Sleeter, Robert Tarjan, and William Thurston provided a proof that the diameter of the n-dimensional associahedron is at most 2n-4 when n is strictly greater than 9. They also proved that this upper bound is tight when n is large enough, and conjectured that large enough means strictly greater than 9. This conjecture has been settled in 2012 by Lionel Pornan.